Welcome, everyone. Thank you for joining us. Wenjun is going to be talking about beta gamma VOAs and 3D mirror symmetry. Feel free to start whenever you're ready.
All right, thanks for inviting me to give the talk. Yeah, please feel free to stop me at any time, and yeah, I would love to hear questions and comments. Great. So today I'm going to talk about this project that I worked on with Andrew Bolling on beta gamma VOA, and we study the category of modules of this VOA using the perspective 3D mirror symmetry. So I think I put the archive identifier underneath, so if you're interested. Great. So this is the outline of my talk. I will first introduce the motivation of this study, and then I will go to introduce the category that we defined, and then I will tell you how we used this mirror symmetry relation to show that this category actually is a braided tensor category. And if I have time, I will talk about matrix factorizations, which is closely related to all these categories. Right, to begin with, our study is really motivated by three-dimensional n=4 abelian gauge theories. And these theories supports topological twists. And we study line operators in these topological twists, and hopefully they're mirror symmetry. So the example that we picked was this well-known one. It's the A twist of a pair of free hypermultiplets with B twist of a single SQED. And the description of the category of line operators is in the work of Dimofte, Garner, Geras, and Hilburn, where they sort of gave like the biggest possible definition in terms of algebraic geometry, and translated into VOAs. The A side, the category looks like modules of this beta gamma VOA. And for the B side, they started with this matrix factorization category, and you can Kourou dualize two of the variables, and that gives you sort of a quote unquote modules of this affine Lie algebra associated to this GL11 Lie superalgebra. And I write quote unquote because this is not correct, because when you do this Kourou duality, usually you lose information because the representation of a Lie group is not the same as the representation of its ghosts. But we'll explain what correction there is in the following slides. Great. So then the question is, what is the category of this beta gamma VOA that should be taken as the category of line operators? So now to introduce this category, we first introduce some objects, some modules of this VOA. So the modules of a VOA is equivalent to smooth modules of the mode algebra. So the mode algebra of beta gamma is a really nice algebra. It's just a tensor product of infinitely many Val algebras. If you wish, the completed version of it. And then you can build modules by choosing a specific module for each copy, and you choose it in a way that is smooth, in that the positive parts should act trivially. So the vacuum module V looks like this infinite tensor product of modules of each copies of the Val algebra. When we choose this to be the vacuum, we also in the convention we work in, the conformal weight of gamma is 0 and beta is 1. Great. And of course there is a symmetry, because you have infinite many Val algebras. You really can't distinguish them. So you can spectral flow each of them, by which what you do is that you take you just move where the gamma acts, where the separation between beta and gamma from 0 to k. Well, in general, you could consider swapping any pair of beta and gamma, but we don't consider that in our paper here. Great. So there is also another set of indecomposable modules, and they are labeled by lambda, which is a complex number, and lambda is not in Z. And in terms of the modules of the Weyl algebra, you can write them in this form. So here, if I view beta as functions on C and gamma as differential on C, or if I view gamma as functions on C and beta as minus of the differential on C, this is just the module generated by x to the lambda. Great. So these are simple modules. In this VOA, there is a U1 symmetry given by the normal order product beta and gamma. The symmetry has level -1. And so previously, there is a category of beta gamma VOA, and they're studied by Rita Wood and Alan Wood. And this category can be characterized by taking all these modules, simple modules, which are spectral flows of vacuum or spectral flow of these W lambdas, and take all the possible modules that have these as composition series and require that J0x semi-simply. So what they were able to show in Alan Wood paper is that this category actually is a rigid braided tensor category. Recall that I said that we were really looking for the category line operators in this topological twisted three-dimensional theory. Our category should be a braided tensor category. Which says that their theorem suggests that this might be a choice, but what we first found was that if we took their category, there is a problem, which is that the endomorphism algebra in this category doesn't reproduce the Coulomb branch. So whenever category I take, if I compute the endomorphism of identity operator, I should be able to reproduce the physical Coulomb branch of the theory. And in our example, the Coulomb branch is just a copy of C, but I'll explain that in this category R, the derived endomorphism is not C. So to show you this computation, let me introduce these two indecomposable objects, but now these two objects are not simple. These are extensions between these vacuum modules. So W0 plus is, they have the following Lowy diagram. So W0 plus has V as a submodule and sigma inverse of V as a quotient module. W0 minus has sigma inverse V as a submodule and V as a quotient. And these are the unique indecomposable that have this Lowy diagram. And this category turns out to have projective modules. And this projective fits into the following exact sequences. And again, as this character uniquely characterizes this projective module P. So what we found is that in this category R, there are actually higher derived endomorphisms between the vacuum, and they can be represented by the following exact sequences. So this map between W0 plus to W0 minus is W0 plus has a quotient that looks like sigma inverse V, and W0 minus has a submodule that looks like sigma inverse V. So there is a map from W0 plus to W0 minus. And similarly, there is a map from W0 minus to W0 plus. And in R, this is that genuinely gives you a non-trivial morphism from V to itself of degree 2K. So that is not the same as what we expect, because the Coulomb branch of this theory is trivial. Great. So, sorry, I see there's a question.
Yeah, let me read it. It says, what is the interpretation of this Coulomb branch in that category?
Yeah, so Coulomb branch, the functions on Coulomb branch is should give me the algebras of local operators. And if my category is the category line operators, I can reproduce the algebra by taking the identity operator and ask what is the endomorphism of that, because that's just the hum between two line operators is local operators that interpolate between the lines. But if you take the identity line operator, which is no line operator at all, then the hum simply just are all the local operators. Does that answer your question?
Wenjun, I think Flo wanted especially to hear that the Coulomb branch is exactly the X algebra of the identity.
Yeah, yes, it's the derived.
So everything is derived. If Wenjun says hom, he means derived hom.
Yes. Yeah, thanks for clarifying that. Yeah. Any other questions? Cool. So the problem that there is this extra higher homs is because of this restriction of J0. So in fact, what this if you look at this exact sequence, this exact sequence actually can be trivialized if you add a module to it. So there is actually a module that has the following Lowy diagram where it has a bunch of composition series and it's indecomposable, and the sort of the composition series just iterate itself. And if you add this object in the category, then you can show then that this map now becomes a co-boundary. So it's zero, it's trivial in the derived hom. So then the idea is that we should add them. And these objects are those that are taken away by this requirement of J0. So this motivated us to define the category, which we call curly sieve beta gamma, to be the category of finite length modules whose composition series are just spectral flows of the vacuum or spectral flows of W lambda. So the category studied by Rita Wood and Alan Wood sits inside our category.
And the condition here, the restriction of J0 is the semi-simplicity condition that you mentioned? Okay,
yes.
Gotcha, thanks.
Yes. Yeah, so for them, proving that R has a braided tensor structure by PZ intertwiners, it sort of they uses this requirement, and so this extra grading is important to them. So yeah, so we see that sort of to have the correct Coulomb branch, the smallest possible extension is this one, and so we want to take this one to be the category of line operators. So there are some new objects in this category. Once I enlarge, once I allow J0 to act non-semi-simply, these W lambdas in a smaller category, they are actually projectives, but in this bigger category, they actually also have self-extensions. So there is a unique degree n self-extension of this object that has the following Lowy diagram. Similarly, the projective P in the smaller category now also has non-trivial extensions, and they have the following Lowy diagram. So if you take the diagonal V here, I don't know if you can see my mouse, but this looks like many copies of P, if you can see. It's a bigger diamond.
We can see your mouse, yeah.
Great, thanks. Right, so the first thing we showed is that our category looks much bigger and seems hard to control, but it's actually not impossible to control it. We show that any object, no matter how complicated it is, it's going to be a quotient of a direct sum of these guys. So our category doesn't have projective modules, but I have sufficiently enough modules to resolve any object. Great. So that sort of gives an understanding of the category by using these objects.
Sorry, what is the physical interpretation of those modules?
So they are like three-dimensional line operators. Sorry, is that what you're asking? Or?
No, I'm saying like, you added some more modules, right, in your category, right? And so it resolved your problem with the Coulomb branch, right? I'm just asking what's the difference in terms of physics? So what did you add? Like, was it like
Sorry.
No, I'm just saying like you added some modules, right? It resolved the problem with the Coulomb branch, right?
Mm-hmm.
So in terms of physics, what did you add? Was it like, I'm just confused. Like, I don't know, maybe some.
So the category, yeah. So if we sorry, let me see. I understand better this language of D modules. So the actual 3D Inc to 4 gauge theory, the idea is that the statement is that this category line operators looks like D modules on the loop space, and this D module, this interpretation sort of comes from this the like infinite many tensor product of L algebras, and like from this 3D perspective, you can what can become a D module on the loop space. You can take any sub variety, and this sub variety then has a structure sheaf, and you can push forward these structure sheaf. And what we did was that and we added like some objects that like are not necessarily just like monodromic, where by monodromic I mean that G0 XM simply. Sorry, I think this is all I understand about this. I don't know if that helps anything.
In 3D, are you taking your theory with the boundary or just like pure, just the bulk part?
Yeah, so sorry. So there are two ways to understand this. So our approach is that we take a boundary condition, a Neumann boundary condition, and we take our line operator and let it stick to the boundary. And then the line operator becomes a module of the boundary VOA. And beta gamma is actually the boundary VOA that we consider that appears on this Neumann boundary condition.
So just one boundary, right? No two.
Yeah, no, not. It's just one boundary. Yeah.
Thank you.
Yeah, thanks. And there's a question from the chat. What is the category of local operation in your framework in slide 7? Oh yes, so here the endomorphism becomes trivial once you add these objects. Yeah. Because like there used to be these higher morphisms. Now, once you have these objects, those morphism becomes co-boundary, so they are trivial. Great. Is there any other questions? Cool. So here we have resolved this issue of Coulomb branch, and this is sort of the smallest category you can cook up to resolve this issue. But there's still this issue that this line operators have collision and they can braid. So this category better be a braided tensor category. And to show that, we use this mirror symmetry relation. this relation, so the idea is that beta gamma is actually related to this affine Lie superalgebra GL1/1. It's described by Krusik and Rieda. And this actually is used by Adamovich and Pedic to compute fusion rules in the smaller category. And the idea is the following. So this affine Lie superalgebra has some simple currents, and they are labeled by a complex number and an integer. And the fusion rules between these simple currents are easy to describe. So fusion of simple currents is still simple currents. And it turns out that beta gamma VOA or beta gamma tensor, a set of BC ghosts, can be realized as a direct sum of simple modules of GL1/1. So this is called a simple current extension of GL11 VOA. And we like to understand this relation as a mirror symmetry relation. Recall that we have this mirror pair. So on the A side, I can choose a Neumann boundary condition, as I was saying. So the boundary, on the boundary, there is a vertex algebra, and it's exactly the beta gamma VOA. And on the B side, we choose the dual boundary condition. It's the Dirichlet boundary condition, and it's perturbatively it's GL1/1. And I should mention that this is the work of Costello and Gaiotto. Sorry, I didn't write it down. But that's only perturbatively. One should extend it by boundary monopole operators. And this is sort of the subtle relation between the ghost algebra and taking the Lie group. They're related, they're co-dual to each other, but they're not exactly the same. And we want to understand these extra modules, this extra extension we take to be monopole operators. And this really works well with the physics computation. So we computed the weights of these, the conformal weight and gauge charge of these extra fields in these currents, and show that, and we were able to show that they actually correspond to the physics computation of De Morphet, Gaiotto, and Natalie Paquet. Yeah, I don't know if I pronounced it right. Sorry about that. Yeah, so then this is telling me that like there is a relation between the two, and this is actually really nice because GL11 because it's a Lie algebra, it's a vertex algebra associated to a Lie superalgebra. It has a really nice category of modules, and it's the Kashtan-Luchti category. It's defined by the category of modules with bounded conformal weight. On this category, it's easier to verify that it's a braided tensor category because you have this bounded below weight restraint. And this extension by monopole operators selects a subcategory. The subcategory is defined by having trivial monodromy with monopole operators. So what was shown in the work of Krusik, McRae, and Yan is that these two categories are both braided tensor categories. And what we use is that we can relate, because my beta gamma VOA is actually a simple current extension, that there is a way to relate modules of GL11 to modules of this extended VOA. So there is a functor, and it's roughly given by a tensor product with this simple current extension. So you view this as a module of GL11, then you can take fusion product, and that gives you a module of the extended VOA. So here I should be very careful because first of all, we have not defined what this beta gamma tensor BC mod is. precisely, to be more precise, I should say that we should first take some kind of a incompletion of KL, and beta gamma tensor BC is an algebra object in that category. So we can consider modules of this algebra object. It's described in the work of Cruzy, McRae, and Yang. Great. Is there any question about this? Cool. So
what is the upshot of this? So you can you go back one slide more? Yeah.
Yes.
So here, it turns out that just the tensor product is just the sum of modules for super algebra, right?
Yes.
Super VOA.
Yes.
And so you use that to use this relation to do what exactly?
Yeah. So the idea. Yeah. Sorry, I didn't specify this. So the idea is that I want to understand whether beta gamma has a nice braided tensor structure, and it's hard to do it just as a beta gamma module, but the goal is to realize this category as something that lives over GL11, because GL11 has a really good category.
So you have more control over it, right?
Yes, yes. So basically, in objects in beta gamma are not don't have bounded from below conformal weight, but once you restrict to GL11 module, the modules of GL11, the category I choose do have this property, and so it's easier to control. And the idea is that once you have this extension, you can just induce modules from the smaller VOA to the bigger one. And that's the approach we're taking. Does that answer your question?
Yeah, thank you.
Yeah, thanks. Great. Yes. So what we were able to show is that, like, actually once you take this extension functor, you look at what is the image of KL under this extension functor, and you can show that they actually map this subcategory into the curly C beta gamma that we defined. So this aspect is just saying that the module category for this BC ghost is just it's very simple. It's just super vector spaces. Great. So the image of L can be thought of as taking Z equivariance, because so here I have a Z lattice of modules of GL11, and their fusion makes it into a subcategory that looks like coherent sheaves on Z, or looks like modules of C star, representations of C star. And this, what this lifting functor does is then that it identifies modules that are related by this translation by Z. So I sort of understand this as taking a Z equivariance. And this L identifies this Z equivariant category with the curly C beta gamma. And this is a 3D mirror symmetry statement, because on the right-hand side, it's a category defined from the beta gamma VOA. That's the A side. On the left-hand side, it's defined from the affine superalgebra of GL1/1, which is the B side category. And as a consequence, this curly C beta gamma is a braided tensor category defined by PZ-20 operators. And this functor L gives an equivalence of not just categories, but tensor categories. So that's the main point of our work, and we sort of understand this as saying that these two categories, both are Brady-Tessel categories because they're both line operators in the topological twist, and they are equivalent. Great. Is there any question?
Can you repeat again? What is scale 0?
Yes. So yes. So I have the category of the Kashtan-Lucci category of GL1/1. It's defined by modules with bounded from below conformal weights, right? And then I have a set of monopole operators, and these monopole operators and the scale 0 are defined by modules that have trivial monodromy with these monopole operators.
How do you think about this, like Z quotient in terms of like monopoles?
Yes. So these fusion structure of these monopole operators give you, so if you take any two monopole operators, the fusion product is still a monopole operator. So this subset of modules on their fusion product give you a copy of basically vector spaces labeled by Z. Right. So I have representations of C star here, and given any two modules, I can ask, okay, if I have one module, I can maybe a monopole operators will fusion with a monopole operator will give me another module, and these two must be the same in the quotient category. They are the same under the lift because the monopole operator is really just a local operator on the boundary. It shouldn't change which line operator it is. So that's why it looks like a quotient by Z.
Is there a star? So in this relation, is there a star? Oh, there's an M, right? The second M.
Yes.
There's a star on it, or is that?
Say it again.
I mean, like you have this sum, right? And there's M, and
Yes.
for the second A, there's minus M, right? Is there like
Yes.
a dot, or what does it mean?
It's just direct sum. So
oh no, I'm stupid. I'm sorry. Yeah.
no.
Just
Yeah, it's
Thank
just
you.
a lattice where I write positive part, negative part sort of together because it's easier to write it that way. Yeah. Cool. I see your question. Oh, sorry. Can you please reshare? Sorry, give me 1 second. I'll share it again.
No worries.
I can't seem to share and make it bigger at the same time. Okay, that works.
Yes, it looks great. Thanks.
Someone's asking how is the Z equivalence derived? So sorry here. So yeah, I should have specified. Once I start working with this bigger category, I have always this. I'm always talking about just the regular abelian categories. Yeah, there's nothing derived here. Yes. Does that answer your question? Cool. Yeah. So that's from using this, we were able to derive fusion rules because fusion rules from the Lee superalgebra is very easy to compute. So if for any element in this curly beta gamma category, if I denote by M subscript n to be the spectral flow of M, then I have the following fusion rules. So the fusion between P's gives me just a direct sum of P's with different length. And similarly, the fusion of W lambda and W mu gives me different W's if lambda plus mu is not in Z. But when lambda plus mu is in Z, or when I have the situation where I have lambda and minus lambda, then their fusion product gives me P. So this P's sort of look like the projectives, but they're each of them is not really projective. Great. So I want to comment that so this category is really labeled by lambda. For each of this lambda, when lambda is not 0, when lambda is not in Z, my category is really generated by these W lambdas, and if you and then the extension between this W lambda with itself is just a simple C. So when lambda is not in an integer, the fiber of my category at this lambda just looks like vector spaces on a plane, but supported at a point. So it's generated by a single element, which is just a structure sheaf of a point, and you allow all possible extensions. And when lambda equal to 0, this category has a more interesting structure. And that's something I think I will talk about now. So is there any questions so far?
Can you explain one more time what is P and what is W?
So P, recall that yes. So recall that I have for the smaller category R, I have a projective object P, and once I allow J0 to act non-semi-simply, then this P itself has extensions. And this Pn just means this n self-extension of P that is expressed in terms of this long diamond. And similarly, this W lambda used to be is a simple module and used to be a projective as well in the smaller category, but now once I enlarge, it has iterated extensions.
What is the second index mean?
This index lambda, you mean?
No, for P. In the last slide you wrote that there is
Yeah,
Pn
so,
and there is a second index.
Yes. Thanks. So the subscript n just means this spectral fluid.
Oh, okay, I see.
Great. Any other questions? Cool. Yeah, seems I have plenty of time. Yeah, sorry, I think I overestimated the amount of time it will take. But yeah, so then I think I'd like to talk about something I'm actually really excited about. It's the matrix factorizations. So I know that probably most of the people here are not really necessarily interested in algebraic geometry. So hopefully I can show you something that is not completely irrelevant. So really, like my understanding of how this is related to the mirror symmetry work of, say, and Justin Hill-Byrne, it is through this matrix factorizations. So the biggest possible category, as I said, it should really look like D modules on K being the algebraic loop space. So K is the space of Laurent series of C. There's a version of D module and that has enough finiteness condition, and that's the category that is the biggest possible one. And sorry, I think, yes. And the B-side category actually looks like some kind of equivalent matrix factorization. So I can take 3 copies of K, and I can take a superpotential that looks like the following function. And here, the X and Y are really the 3D hypermultiplets, and A is the gauge potential. And there is a K star equivariance where K star act on XY with opposite charge and K star act on A just as how a gauge group would act on the gauge field. So the biggest possible category should look like K star equivalent matrix factorizations. So the nice thing about this is that it actually it's due to many interesting categories. Say if I only dualize X, then the superpotential will set the rest of the part to be 0. So it sets that partial Z plus AZ multiplied to YZ is 0. And we interpret that as line bundle with a connection and a flat section. So I'm considering line bundles on D star, which are all trivial. So giving a connection is the same as just giving this function A. And this whole thing being 0 just says that the connection act on Y is 0. So Y is a flat section. So one of the very hard algebra geometry object result of Hilbert and Raskin is that if you take the coherent sheaf on this moduli space, and that's equivalent to D modules on K. And that's a very, very hard algebra geometric result. And the problem is that these two categories do not have braided tensor structure. They are very, very big. And this equivalence for them is equivalence of chiral categories, which is something rather mysterious to me, at least. So to get GL11, we sort of dualize both X, Y, and we dualize ghost from K star. So if we dualize X and Y, then the superpotential W is trivial, but then you get a non-commutativity between the dual of X and dual of Y, and this del Z plus A just simply gives you the computation relation of GL1/1. And the field in GL1/1 that's called N comes from the dual of the ghost of K star. Right. So that's to me, like, I felt like this category is a very useful one because it sort of connects all the different approaches of this 3D mirror symmetry. The problem is that this is not a well-defined category because the problem is that taking K star equivariance is not a very well-defined action. If the group is smooth, then it's easy to define it, but K star is also not smooth, so it's very hard. And it might be chiral, and hopefully these are equivalents of chiral categories. But what I want to say is that there is a way. Yeah, sorry. First, let me say that. So the categories that we studied, the category of beta gamma as well as the Cauchy-Lucci category, they sort of come from some kind of finiteness restraint from these big possible categories. So I can say a little bit about GL1/1. So the Cauchy-Lucci category can be thought of as this matrix factorizations that is supported on regular singular connections. So instead of looking at all possible A of Z, I look at A of Z such that it looks like A divided by Z. So it only has the regular singular part. And if I only look at that part, then could you dualize this category? That will give you the Cauchy-Lucci category. Similarly, there is a restriction on the A side that gives us this beta gamma category that we consider. And then the thing is that by restricting to this smaller category, by giving these finiteness condition, it allows fusion and braiding. Now, it's nice that this category is actually also related to quantum group. And so again, we choose the smaller subcategory that is regular, that has regular singular connection. So we are going to change the perspective where we will exponentiate the connection. So we don't care about the connection anymore. We only care about the monodromy. And when we do that, so this category really just looks like the category of equivariant matrix factorizations, now not only a big infinite dimensional space, but on a nice finite dimensional space. So I have C star times C, and there is a potential that looks like Z minus 1 times XY. So the C star only acts on X and Y with opposite charge. And so now by restricting, and we were able to cut down this big matrix factorization to a finite dimensional thing that is right now well-defined, because there is no non-smooth group anymore. And it turns out that this also has a very well-defined monoidal structure that happens to be symmetric. And the nice thing is that this actually is related to quantum groups via a Kourou duality. So if we Kourou dualize X and Y, we get two odd variables, and the superpotential gives me a non-commutativity relation that says that the supercommutator of these two odd elements is Z minus 1. So if you take Z to be, so in this quantum group, there's this generator K, E, and F. So if you take Z to be K squared, and X to be E, and Y to be K of F, then that's exactly the commutativity relation of quantum groups. So in conclusion, one actually has a really nice functor from this quantum group category to matrix factorizations that and we should check that this actually preserves the monoidal structure for both sides. And so my hope, the hope I had was maybe this will give me a way to actually connect quantum group to all these big VOA categories that we have been considering. But again, this is only like a first step towards that. So the question I have that I don't know how to understand is how to translate braiding and twist from one side to the other. Great. I think that's all I have to say today. So
thank you so much. Perfect timing, by the way.
Thanks.
Okay, thanks so much. There been a lot of questions, but if you have a question, please feel free to unmute yourself. Oh, there's one in the chat that says, what's the rank of the matrix X, Y here? Thanks.
Which matrix? So sorry, X and Y are fields, they're not matrices. So in this slide, X and Y are just numbers. Yeah, I shouldn't say C2, X, Y in C, sorry, that's a typo here. And here, this big capital X and capital Y are Laurent series. Yeah, so they're all one-dimensional.
Thanks. Let me stop the recording so